All right, grade 10 has a revision of work calculations to calculate the energy required to move objects. I thought I'd make a little series of videos again to show us how to work through this so that we can then apply it in our problem sets and labs in the next couple weeks. So in class, you guys told me last class that work relates to energy and work is MAD, or the force that you apply an object to push it a certain distance. And the units that you're going to measure for work relates to joules. Those are just things I wanted you to think about before we start. So how would we solve the work required to pull objects? Okay, and often when we're pulling an object or dragging it across a floor, we're not pulling it, we're not getting down on the floor and pulling it in that same direction parallel to the floor. We usually attach a rope and we drag that object across the floor. So how do we work, and how do we calculate work in a situation that looks like this? Well, you got to remember that everything is a vector when it comes to forces. So work, as you guys told me, is equal to force times the distance or the displacement that I move an object. And what needs to happen is that force has to be in the same direction. So force must be in the same direction as your displacement. Okay, so that is a very important thing for you guys to know when you're looking at this situation. So we need to find out how much of that force that that person is pulling that object up with is going to be pulling in that direction to slide that object in that direction. And this diagram has kind of explained it to you. Your applied force is your hypotenuse in that triangle. And the force that is parallel to the direction that that's sliding is your adjacent to that triangle, and this is opposite. So in order to solve that adjacent hypotenuse, okay, we use a cosine relationship. So let's say that I am pulling that rope with 100 newtons. Well, the amount of force that I'm actually pulling horizontally with is going to be equal to, so just remember that cosine theta is equal to my adjacent over my hypotenuse. So in order to solve for the adjacent side, okay, adjacent is going to be equal to cos theta times my hypotenuse. That's what it's saying over here. So to solve for the force in that direction, okay, that force is going to be, the force horizontal is going to be equal to 100 newtons times cos theta. So imagine that this angle was 30 degrees, my favorite angle to look at, okay? Then the force that you'll be applying is equal to 100 newtons times cos of 30 degrees. And if you solve that, it should be somewhere around 86.6 newtons. Okay, so this dude is pulling that object with 86.6 newtons. So in a way, to calculate the work, I would take the force that I just calculated, 86.6 newtons, and multiply it by the distance that I'm going to drag that object. That's what this equation is saying here. So often in textbooks, you would see this equation for work, where work is equal to FD cos theta. And that cos theta represents the component of the force that you're pulling in the horizontal direction, and D is the total distance. So if I pulled that object, if let's say D is equal to 10 meters, okay, well then my work is going to be equal to FD cos theta. Okay, the work is going to be 100 newtons times 10 meters times cos of 30 degrees, if that was my 30 degrees like the last problem. And then we're left with the work that I had to do was 866 joules. And that's how I would solve how much work I had to do to drag something across a floor. So where does that work energy come from? Well, it's going to come from the chemical energy, the food that this person has eaten throughout the day and converted into ATP, or energy. And you have to convert that energy to be able to make your muscles contract and apply effort to move that object a certain distance. So in one of our labs that we're going to be doing, you're going to start to figure out how to make a food or a diet plan to figure out how much food do you need in a day to do the tasks that you generally do in a day. Okay, and this is going to be a very important thing that you're going to look at in order to analyze the types of motions that you're doing in daily life. Okay, so here is another question, the same situation. This man is pulling his daughter with a 50 Newton force at an angle of 30 degrees, and he's pulling her for a total distance of 30 meters. So if I wanted to calculate the work, just pause this and see if you can do that. All right, so notice that he's pulling with 50 newtons, despite the fact that she might have a weight of 500 newtons. Okay, he's pulling her with 50 newtons, and he's able to move her because there's wheels, all right, and quite low friction. So I don't have to worry about factoring in friction or whatever. The force that he's pulling with is the force that I'm going to work with. That's the force he's using. So the force that he's applying times the distance is going to tell me the work that he is putting into that. Okay, so in this case, I need to solve the force that is in the horizontal direction. So work is going to be equal to, let's get back to green, FD cos theta, as we said at the top. So work in this case is going to be 50 newtons times 30 meters times cos of 30 degrees. And what does that give us? So let's just work this out. Okay, so 50. Notice that I'm saying work in many ways. It's so funny. It gets in your head. Work. All right, so in this case, the guy puts in 1,299 joules. Okay, a little bit more work, but that's because he went a larger distance. All right, and he would have to, again, get that energy from somewhere. And that would be in the form of chemical energy. So that's sliding or pulling objects. Let's look at lifting objects. And you guys have done this already many, many times. How do I calculate the work that this guy's got to do to lift 50 kilograms of weight, a total of 50 kilograms of mass for a vertical distance of 2 meters? How would you do that? Pause the video and see if you can do that. Well, assuming that he is lifting at a constant velocity, that's important, because if he's lifting at a constant velocity, the force that he is applying is going to be equal to the force of gravity. Okay, so at constant velocity, my acceleration is equal to 0. That means that my net force that I'm applying is equal to 0 newtons. So that means that the applied force minus the force of gravity is equal to 0 newtons. That means my applied force is equal to the force of gravity. That's important because we need to figure out how much force is this weightlifter going to apply to lift that mass. If he lifts it at a very constant speed, that would be the force that he's applying. If he's accelerating, this is like powerlifting and he's launching it up there, then he's going to be applying the force of gravity plus ma, the acceleration that he would apply to actually accelerate that. So the minimum force he'd have to apply is the force of gravity, and then he'd have to add 50 kilograms times whatever acceleration he is applying. So you'd be doing more work if you accelerated than if you lifted at a constant velocity. But let's just assume that he's lifting at a constant velocity, so the force of gravity. So in this case, the work that he's going to apply is force times distance. I don't need cosine or anything because the force that he's going to be applying is in the same direction. So there's no cosine in that. All right, so the force he's applying is the force of gravity, so m times g times d, okay? And in this case, it's going to be 50 kilograms times 9.81 times 2 meters, okay? And that works out, the work in this case works out to, 981 joules. Now, let's talk about sliding objects across a floor with friction. All right, and again, let's look at it in terms of constant velocity. So I'm just applying a force that allows me to push this at a constant velocity. It's not accelerating. So in that case, because there's no acceleration, the net force is equal to 0 newtons. And I need to understand what forces are on this box. I got the force of gravity, I have the applied force, and I have equal and opposite force of friction. So in this case, for that to be a net of 0, my applied force that dude is applying, subtracted by the force of friction, is going to be equal to 0 newtons. So then your applied force is equal to your force of friction. Okay, and that's important because what is friction? Well, the force of friction is equal to the normal force times mu, if you remember from previous work that we did. So then the applied force that this guy is going to be pushing is equal to the normal force that the floor is pushing up with times the friction coefficient. And then the normal force in this case is equal to the force of gravity. Okay, so just take a step back and review friction that when we were doing those calculations. So for this person to slide that object at a constant velocity, he needs to apply the force of friction, which is going to be the force of gravity, or the normal force, times mu. So let's put some numbers in here. Okay, let's assume that the mass of the object is 10 kilograms. Let's assume that the force of friction, or the friction coefficient, is equal to, the friction coefficient is equal to 0.5. Okay, he's pushing so that it's going at a constant velocity, and the distance that he pushes this is 10 meters. Okay, so with all that, how much work is he going to have to do? Well, in this case, work is equal to the force that he applies times distance, because he's pushing in the same direction. I don't need no cosine stuff. So the work is going to be equal to, and now the force that he's applying is my force of friction. So it's going to be equal to Fn times mu, that's the force of friction, times 10 meters, which is the distance that he put in. So the work is going to be equal to 10 kilograms times 0.5, which is the friction coefficient, times 10 meters again. And now the work is going to be equal to 50 joules. So 10 times 10 is 100 times 0.5. So it would take him 50 joules to slide 10 kilograms, 10 meters across the floor. All right? And that's that for some basic calculations on work when we're moving objects in reality.